Okay, so hi, thank you very much for giving me the opportunity to talk today. For those of you who don't know me, my name is Robert Stein. I'm a graduate student currently at DAISY in Berlin, but soon to be a postdoc at Caltech. And today I'd like to talk to you about a recent work that we published in Nature Astronomy called a tidal disruption event coincident with a high energy neutrino. And knowing the audience a bit, I thought maybe I'd start with the end of my title and just briefly introduce high energy neutrinos themselves. So our story actually begins about 100 years ago with Victor Hess and his famous balloon experiments. And he was the first person to discover that the Earth is actually bombarded by charged particles known as cosmic rays. And in the intervening century, we've built bigger and bigger detectors and learned that cosmic rays can have extremely high energies of 10 to the 19 or 10 to the 20 electron volts. And what that means is that somewhere in the universe, there are extreme cosmic accelerators, which are capable of efficiently accelerating particles way beyond what we could ever achieve on Earth with something like the Large Hadron Collider at CERN, for example. And so, of course, we would absolutely love to know, like, what are these cosmic accelerators? Where do these cosmic rays come from? But unfortunately, because cosmic rays are charged particles, that means that they are deflected when they travel through the universe, as you can see in this illustration here, which means that even if you could detect a cosmic ray and reconstruct it perfectly, you still wouldn't work out where that cosmic ray actually came from originally. And so that means that we need to use other tools or other messengers in order to try and unravel the mystery of where these cosmic rays are actually coming from. And I guess the first thought you'd have if you can't look directly at cosmic rays is you go for the trusty photon. But unfortunately, at these very, very high energies, photons actually get absorbed extremely easily. So it is very difficult to detect a photon that would come from a cosmic ray acceleration site. But fortunately, there is another messenger, and this is the one I want to talk about today. This is the neutrino. So neutrinos are weakly interacting neutral particles, which means that they travel very nicely in straight lines and don't get absorbed very much, and usually can make it all the way back to Earth. And the other nice thing about neutrinos is that they are only produced in these cosmic accelerator sites. So if you work out where neutrinos are coming from, you are sure these are cosmic accelerators that are also producing cosmic rays. So in principle, it's easy. You just need to find out where neutrinos are coming from. Unfortunately, the things that makes neutrinos great messengers makes them very difficult to detect because they are weakly interacting and electrically neutral. So you need to build an absolutely enormous detector to have a hope of even detecting one. And the most enormous neutrino detector on the planet is the IceCube Neutrino Observatory, which is located at the geographic South Pole in Antarctica. It's shown here on the left. It basically covers 1 cubic kilometer of ice. So this little smudge in the lower right of the image is representing the Eiffel Tower. And it's basically a block of ice filled with photomultiplier tubes, 5,000 of them, that can detect light that is emitted in the detector volume. And what you hope is that a neutrino passes close by to the detector, interacts, passes through, and then emits some light. And it might look something like this on the right. And so this detector has been built and these neutrinos are being detected. And then the question becomes, where are the neutrinos actually coming from? And one way to do that is with electromagnetic follow-up observations. So I'd now like to talk very quickly about ZTF, although you already heard about this yesterday, for example, in Anna's talk. So ZTF is an optical telescope at Mount Palomar, California, with an absolutely enormous field of view. You can see that on the right, 47 square degrees. And ZTF is really an industrial transient discovery engine. So it basically knows everything that happens in the northern sky to a depth of 20.5 mag because the sky is surveyed every 2 nights with ZTF. And what we would like to use ZTF for at DAISY is looking for the sources of neutrinos. So when a neutrino is detected by IceCube, the neutrino direction and time is reported publicly and automatically. And then we take ZTF, we point in the direction of the neutrino, and then we hope through our follow-up program to magically find an electromagnetic counterpart at the end. And of course, the way I've illustrated it in this figure makes it look very complicated, but it's not actually a magic black box at all. If you open it up, what we do, ZTF will detect something like 500,000 objects in a night, but once you remove the stars and the asteroids and planets, and you only look at things that are really in the footprint of the neutrino event. So neutrinos are usually localized to roughly, say, 10 square degrees or so. then you don't have so many objects left. And then of these objects that you do have left, what's really most important then is you can spectroscopically classify all of them. And then for each candidate, you look at the spectroscopic typing and say, does this object belong to a population that has been predicted to maybe produce neutrinos? And by following this chain, then you hope at the end to be able to find a counterpart. Now, I mentioned possible populations. What might that look like? We've already heard about several of them at the meeting. So gamma ray bursts or supernova, possibly with choke jets or with CSM interaction, or active galactic nuclei, particularly blazars, or as you may have guessed from my title, also tidal disruption events. So these are the sorts of things that we're looking for with our program, which could be candidate neutrino sources. So just to give you some statistics on the program, ZTF saw first light in March 2018. And so when we published the paper, then the statistics were complete up to February 2020. So it's a bit out of date now. But as of that time, there were 31 neutrino events published by IceCube, of which we had followed up 8. And basically the ones we did not follow up, there were a few too close to the sun, a few that were retracted, and others that were just generally not super high quality neutrino events, so ones that had relatively low probabilities to be astrophysical. And you may already notice on the table on the left, there is this one neutrino event that is highlighted very suggestively in bold, and this is IceCube 1910-01A. And this is, of course, the neutrino that was, in fact, coincident with a tidal disruption event. And so that's what I would like to talk about for the rest of my talk here. So the tidal disruption event itself was known as AT 2019 DSG. And so the first thing to say is that it was discovered by ZTF as part of ZTF's systematic search for neutrino for tidal disruption events. And if you want to know more about that, also Yuhan Yao has a poster at this meeting, which is also covering the same topic. And so what's great about this program is that meant that there was already a lot of data on the source even before the neutrino was detected. So the neutrino is illustrated on the x-axis here with the dotted line, and it arrived roughly 170 days after the TDE was first discovered. And so once we found this object, obviously the first thing you do is you try and throw every single observational resource that you can at this thing to really understand as best as you can what might be happening, whether something special is happening at the time the neutrino was detected. And what we saw is that for this particular event, basically it looked mostly like a regular TDE. So in terms of most TDEs, they were well described by thermal emission. This one was too. The black body temperature inferred was a little higher than average. The luminosity was a bit higher than average, but it was not really considered extraordinary based on the broader ZTF sample of tidal disruption events. What was a little interesting in particular, though, is that this source was relatively bright and also pretty close by. And then obviously, when you put those things together, that meant that in terms of volumetric energy flux, this was one of the brightest TDEs. One other thing that was very interesting about the source that we found is that this source was actually detected in radio, and that is not a ubiquitous property of TDEs. So again, there was observations preceding the neutrino detection. So that's the 3 colors on the left there. And then the very last one was taken after the observation of the neutrino. And so we wanted to understand if there was any temporal evolution in the radio properties of the source. And as you can see on the figure on the left, yes, it evolved quite a lot over the course of the observations. So the observations reveal a synchrotron emitting outflow. And so we also try and infer the properties of this. So we see an outflow that is expanding, and in our data, it seems to also be expanding quicker at late times. And also there's a lot of energy relatively being put into the outflow. So you can see that on the panel on the right. And also maybe another thing more relevant to this specific meeting is what we were really nicely able to do is have a complete spectroscopic history of this object. So it was observed many times as part of the ZTF program. And in particular, we got extremely lucky to get a Keck spectrum with ARES just 1 week before the neutrino arrival time, entirely serendipitously. And obviously, once the neutrino came, then we took another spectrum and we wanted to make sure we could really understand whether there had been any particular evolution. And in this case, unfortunately, there wasn't any evolution, but it was very nice to very concretely be able to rule out that there was anything interesting happening spectroscopically that was coincident with the time of the neutrino. And that's something useful that we can know for future observations. So maybe just to close, because I think I'm basically out of time now, why is this interesting in general? And I think the take-home message is that TDEs in general are very rare. So the fact that we found one coincident with a neutrino, it's very unlikely that that would happen by chance. So we calculate the probability is just 0.2%. And if it's not by chance, then obviously the only alternative is that this is really an astrophysical association. And what this result suggests to us is that TDEs are important cosmic accelerators, the cosmic accelerators I talked about at the start of the talk. Okay, I think I'm really out of time now, so I will just leave up my summary and say thank you very much for your attention, and were there any questions?
Thank you. Do we have any questions here or online? No questions online? Any questions here? So can you say a few words about the localization capabilities of IceCube? You mentioned 1 or 10 square degrees. I forgot the exact number.
Yeah.
What is the limit there?
So basically the limit is to do with how far the event passes through the detector. So I can maybe just show you the event view here. So basically, depending on the lever arm, like how far the track goes through the detector, you can localize them more or less well, but it's typically between 1 square degree for a very high energy event or 10 square degrees, depending on the angle and stuff. Because the ice is very inhomogeneous, unfortunately, because this is more, it's not like a perfectly sort of calibrated optical telescope, it's nature's detector.
So are there any plans to improve that? So do you need to duplicate the IceCube and some other, local and?
Yeah, so there are plans at the moment to have the IceCube upgrade, which is going to be an infill array. So it's a few additional strings very tightly packed together in the middle of the ice, and they will be absolutely full like a Christmas tree with calibration devices to really try and model the ice as well as humanly possible. It's already basically the best studied cubic kilometer of ice on the planet, but we want to do even better. And so, yeah, that should enable us to better understand exactly the structure of the ice, where dust is, and so on, and then better calibrate the direction of neutrinos that are detected.
Great, thanks. We have another question here.
What's the reason for the delay between the optical tidal disruption event and the neutrino arrival?
That's a good question. So this puzzled us at first, but I think, the emission of neutrinos is a non-thermal process. And so I think basically the light curve that should guide your eye is the this non-thermal radio emission instead. So if we look at the outflow and the activity of the central engine here, it seems to be roughly constant. And so from this, you wouldn't be surprised to wait a while to see the neutrino. And so it kind of suggests that the optical light curve is not the best proxy for exactly when the neutrino should arrive.
All right, any other questions online? No? All right, let's thank the speaker again.
Thank you.